Now that you know what photogrammetry is, let's look at how photogrammetry software works. To join our global pilot network, register at inflights.com/pilot. The photogrammetry software recognizes pixels in multiple photos and then stitches them together and creates 3D points in space. It is very important to capture every part of your subject, because photogrammetry software needs at least 3 images with the same feature to reconstruct it. The photogrammetry software uses the parallax effect. This means that the dataset should consist of many images taken from different perspectives. In the first part of the photogrammetry theory video, we told you about parallax effect, but just to remind you, parallax is a visible shift in an object's position when it is viewed from 2 or more different angles. It allows for distance and size estimation of the object. Photogrammetry software uses structure from motion algorithms, in short SFM. SFM is a method for estimating 3D points from 2D images. This method is similar to how humans and other animals see in 3D. We perceive 3D objects by moving around the object. This is called motion parallax. Parallax in photogrammetry software gives ellipsoid error. Ellipsoid error is the measure of uncertainty of the point's position in XYZ coordinate system. Ellipsoid error impacts the accuracy of the final results. To minimize this error, you will need to take images from different angles. Don't forget that each image needs to overlap with the previous one. By combining all mentioned methods, the software can determine automatic tie points. Those are characteristic features between 2 or more images. Those automatic tie points are 3D points in space. The photogrammetry software computes hundreds or even tens of thousands of those points, depending on your dataset. These many tie points are called sparse point cloud. It is used to align the project. In this processing step, we use ground control points and sometimes manual control points to improve alignment and correct georeferencing of the project in a selected coordinate system. The alignment process is the most important step in processing photogrammetry data. It directly impacts the quality of the final results. After the alignment process is done, the software usually computes densified point cloud. The densified point cloud is a densified sparse cloud. From densified point cloud, other outputs are generated. So what are the limitations of photogrammetry? Shiny and smooth materials, for example shiny metals, and plastic surfaces, overexposed or underexposed parts of the image. Single color materials lacking any physical texture, for example white walls. Transparent glass surfaces, for example skyscraper walls. Mirrors. Water, for example river. Let's look at the dataset quality. It can be divided to image quality. The images that you take must be in focus, not blurry, with low ISO noise and right amount of contrast. Exposure of the image. Every image should be properly exposed. This means it should have just the right amount of light, and the exposure should be consistent for entire dataset. Image texture content. It determines the amount of tie points that the software can find. If there is a homogeneous textured surface in your dataset, then photogrammetry software won't find many tie points. Image overlap. How much each image overlaps with the other. Is every feature visible on at least 3 images? Image GSD. The distance between 2 neighboring pixel centers measured on the ground. Coverage of the area that you want to map. Your mapping mission must be larger than the area of interest. This is a common mistake when a pilot creates a photogrammetry mission the size of the area of interest. Your photogrammetry mission must be bigger. Motionless subject. You want your subject to be stationary. For example, when mapping a real estate, make sure that the windows are closed throughout the dataset acquisition. Image texture content. Photogrammetry software works best with texture-rich, multicolored surfaces. If your images show a homogeneous, smooth or reflective surface, the final result will likely be deformed or have holes in those areas. Overexposure and underexposure also causes the image to lose texture in those areas. Check out the previous video where we explained camera settings. Now let's look at exterior orientation. This is position and orientation of the camera when the image was taken. Those parameters are gathered by the built-in GPS module and inertial measuring unit and are usually written in your image metadata or in a separate file. So let's have a look at it closer. Drone GPS accuracy. This information helps to determine where the image was taken. The standard GPS receiver in most drones, like consumer DJI drones, has the same accuracy as your smartphone, and it is accurate up to 5 meters with a good GPS signal reception. RTK and PPK systems are more precise and much more expensive. Those systems can georeference your images with few centimeter accuracy. However, you can still use consumer drones like DJI Phantom 4 Pro and achieve good absolute accuracy of your project, but you will have to use much more ground control points. Inertial measuring unit accuracy. The IMU uses one or several gyroscopes to detect changes in rotational attributes like pitch, roll, and yaw. This information helps determine where the camera was pointed at. Timestamping of the images. Timestamping technology ensures that the image metadata has the correct position from the GPS receiver and IMU. Basically, it writes the accurate position and tilt of the camera at the exact moment when the image was taken. The more accurate the exterior orientation measurement is, the less ground control points are needed in your project. That's it for this video. Please watch this video a few times and see you in the next one. To join our global pilot network, register at inflights.com/pilot.